In this video, we will learn about graph search and traversal algorithms. Why we are telling that both search and traversal will be carried out using same algorithms is, if you want to search for a particular number, while you are traversing itself, you will be able to find whether that particular number is existing or not. So same algorithm can be used for search and traversal actually. So there are two different types of search and traversal algorithms, that is breadth first search and depth first search. So with examples we will learn how we will be performing breadth first search and depth first search. So basically here illustration we are seeing for breadth first search. So what we are going to see here is adjacent nodes will be visited first, and then we will go over the adjacent nodes of the existing nodes actually. So let us see how BFS will be carried out on a graph. We are seeing on the undirected graph. The same process can be carried out in the directed also. So we are starting with the node A, and here we require two arrays, we can say, that is visited and queue. So first we will, whenever we come across one particular node, we'll copy into visited. Corresponding adjacency nodes we'll put into the queue. Let us start the process. So we are starting with A. So insert A into queue. So first, because initially we are going to start with the queue, everything will be going from the queue to the visited array. So front we are pointing to A. Front pointer and rear pointer we will be having in the queue. We all know about that. So front will be pointing to A. Now insert A into queue. Then whatever you are having which is pointed to front, that you have to delete and pass it to the visited array. So delete A from the queue, mark it visited, and insert neighbors of A or adjacency nodes of A into queue. So what are adjacency nodes of A here? B and D. These B and D you can insert into the queue in any order. You can insert first B, then D, or you can insert D first and then B. Okay. Now, so from Q, you are going to push that A into visited array. Adjacent nodes of A, B and D will be inserted. So here we have B, and then first I have inserted B pointed to front, and then D rear is pointed. Now because we always delete the elements using the front pointer from the queue, B will be pushed to visited. And when you are pushing the B, like deleting B from queue and inserting into the visited array, neighbors of or adjacency nodes of B should be inserted into queue. So here neighbors or adjacency nodes in the B is like a C and E. So that will be pushed. Again, order doesn't matter. Now delete B from queue, mark it visited, and insert neighbors of B into queue. So B is copied into visited. We have deleted that from queue, and C and E we have inserted. Now because B is deleted, front will be moved to D actually, and rear will be pointed to E node. Now obviously we are supposed to delete D, and when we are deleting D from queue and inserting into visited, the neighbors of D should be copied into queue. But what are neighbors of D? B, C and E. But already B is visited and C is in queue actually. So we need not do anything. Just delete D from the queue and mark it visited. Okay. We are writing because it is common procedure, but in this particular example, D can be just deleted and inserted into the visited array. Similarly, next C will be deleted. Then E will be deleted. So when you are deleting E, front will be pointed to the, like it is beyond the queue size actually. So what will happen? Front is greater than rear, which indicates that queue is empty. So when queue is empty, it indicates that all nodes in the graph are visited actually. So your BFS of this particular graph is A, B, D, C, E. Okay. Then same graph we are considering as an example. Let us see how we can perform the DFS. And here you can observe that we are using stack. In the case of BFS, we have used Q, and here we are using stack actually. So what we will do, DFS, depth first search. So deep into the graph we will go, then we'll come back to the above level, and again deep will go. Like this it will happen. Let us see an example. So again I'm starting with A here. So push A into the stack. So we'll push A into the stack, and A is pointed with the top of the stack. Now what we have to do, we have to delete the element from the top of the stack, push it to visited array. Corresponding neighbors should be pushed into the stack. Now what we will do, from stack pop A, mark it visited, and push neighbors of A into stack. So A will be pushed into your visited array, and B and D can be pushed into the stack. Now here I have pushed first B, then D. Again order doesn't matter, you can push D and then B also. Okay. Because top of the stack is D, obviously like we can pop D only, because stack is always last in first out. So D should be popped out. So pop D from the stack, mark it visited, and push neighbors of D into the stack. So what will happen here, when you are popping out D, neighbors C and E are there. So you can push C and E into the stack. Again the order doesn't matter. So you can see D is removed from stack and it is copied to the visited. So C and E will be existing here. Now because top of the stack is E, you pop out that from the stack and copy into the visited array, and neighbors are C, B, D, and D is already visited, B and C are already in the stack, so we need not do anything. Just pop out from the stack and copy into the visited like this. Then pop out C, then pop B, then if you observe, top of the stack is -1, so it indicates the stack is empty, so which indicates that you have visited all the nodes in the graph. So the DFS is A, D, E, C, B for the given graph actually. Okay, so as you have observed that in some cases, in different orders also we can push the elements into the stack. The DFS of this particular graph is not only this. This is not the only solution. We can have different DFS for a particular graph actually. Okay. Thank you.